we've just got this, homework 11. I think there's maybe a misprint on this assignment I've just given you, flood control. It says homework 10. I think that's actually homework 12. So you can cross that out on the paper where it says homework 10. Does everybody have a copy of the assignment? So this is the last homework assignment of the semester. Yeah, nice, right? So there's two problems from the textbook, and we'll go over the problem-solving related aspects of this chapter in class on Thursday. And then just some things I'd like you to do on a website that I'll briefly demo today. So the way it's going to work for the rest of the semester is we've got today and Thursday is chapter 14, flood control. And then the week after Thanksgiving, we'll have 2 class lectures, and that'll all be about subsurface hydrology, which is the movement of water underground. And there won't be a homework assignment associated with that. We'll do a couple of in-class exercises just so you can get some exposure to problem solving. And then the week after that, we've got final exams. So it all comes together pretty quickly. Any questions related to the schedule for the rest of the semester? All right. Well, let's talk about design scale. And you've already heard about the return period of storms, like you know the difference between a 2-year storm and a 25-year storm. And you know that a 25-year storm is going to be bigger because it's the type of storm that is so large it only comes around on average once every 25 years. Or in other words, in one given year, there's a 4% chance of a 25-year storm coming around. Well, how big the storm is that we select is one of the main factors that we choose for hydraulic design. And so there's safety considerations, and there's also trying to balance the cost of the damage that might be caused if the structure fails with the cost of constructing it. So you wouldn't want to construct a $10 million levee to protect a $1 million field, for example. So you're trying to balance how frequently something is going to be damaged and its value with the cost of protecting it. And sometimes we have to move beyond the idea of return period storms for the really, really long duration into what's called estimated limiting value. And in the design of a dam, for example, you don't plan on a dam failing once every 2 years or once every 25 years in the same way that it's okay if a culvert fails every 25 years, because when a culvert fails, all that really means in many cases is the water will flow over the top of the road. And you know, we can handle that every 25 years, but we don't want a dam to break every 25 years. And so there's a different way of looking at storms when you're designing these really critical structures, and ELV, you can think of that as the maximum storm that could possibly happen. And the way they determine the storm size of that nature is by looking at the maximum saturation capacity of air, you know, how much moisture actually can be in the air. It can't be 100% water up there floating around. So there's a maximum solubility of water in air, and they look at if several storms are colliding all at once, all of them with that maximum saturated air, how much water could fall out of the sky over how big of an area. And so what this figure is showing is that for minor structures like culverts, maybe you'll design it to fail every 2 to 100 years. That would be the frequency with which you want your structure to fail. But then a major structure like maybe the Bluestone Dam here in West Virginia, it's called Bluestone, right? For a second there I thought Bluefield, but it's Bluestone. You wouldn't necessarily have the same tolerance, and so you'd maybe design a major structure like that so that it can handle the amount of water that would come maybe up to the total limiting value for the maximum size of the storm. And sometimes ELV is interchangeable with another phrase that's called probable maximum precipitation. So PMP is another term that's, you would use the probable maximum precipitation in order to determine what is the estimated limiting value. So this is the rainfall that's going to give you the runoff amount that is associated with estimated limited value. So it gives you an idea of what some of the typical return periods are used for different types of structures. So you'll see maybe in urban drainage, a storm sewer might have between 2-year storm to 25-year storm in a small city. Huntington, I think, would be counted as a small city. And unfortunately, the storm sewers in Huntington fail far more frequently than this. There are storm sewers that fail in Huntington multiple times per year just because there's so much urbanization and the pipes are so old and so small that there's more water getting to the pipes than can handle. And so, as a result, water backs up into people's homes and businesses and cause a lot of damage. Here it's saying that small dams would maybe be designed with the 50% of ELV in mind. A small dam could mean usually one that would have 8 feet, 10 feet of water that it's holding and not a big urban population downstream of it. So what we're going to do on Thursday is we're going to be looking at trying to select alternatives for protecting life and property that best match the economic value of what they're protecting and also the cost of damage if it occurs. And part of our calculus when we do that, part of what we're weighing on the scale is how frequently we think things are going to fail. And so the main point of this is just to show sometimes we go beyond the return period way of looking at things and we start looking at as a percent of ELV instead. All right, so here's a curve that shows design life on the x-axis and then return period of a storm on the vertical axis, and then here is going to be the probability of a certain storm happening. And so let me just illustrate how this works and then we'll talk about what it means. So a 10-year design life. If you expect something is going to last for 10 years, like maybe a car would last for 10 years. If you have a 10-year design life and a storm of a 5-year storm, if you go over here and find the intersection of the two, it's pretty close to 0.9. And so what that means is that if you expect it to be around 10 years, then there's about a 90% probability that during those 10 years you'll have a 5-year storm occurring. And so if we go to a 10-year storm, so if we go up here to the 10-year storm, you'll notice, let's see, the 10-year storm, we go over and up, there is about 63% risk of a 10-year storm or larger. So you would maybe think that there'd only be a 50% risk of a 10-year storm happening in 10 years. But it's actually a 63% risk of a 10-year storm or larger because each year is cumulative. There is a 10% chance in each individual year, and the cumulative risk means that that the probability of the storm is maybe when you have a continuous number of years larger than any one given year. So here's another illustration. If we have a 20-year design life, what storm size has only a 5% risk of at least one event? So a 20-year design life, if we go over here, we want to know what's the 5% risk. And so up to the 5% risk, it's a 500-year storm that there's only a 5% risk. And so it's important to have at least a basic appreciation for probability, and that'll come into play a little bit more when we do the calculations on Thursday. We'll come back to this and actually try some calculations. We've looked at rainfall data before, but it's worth revisiting the idea that there's different ways to organize data, even when you've got the same data set. Here is, at the top in Figure A, a complete set of rainfall data over the course of a certain number of years, 20 years. And so it's showing that in some years there's a lot of really big storms, and then there's a couple of years where there's not much storm activity. You can look at what is the top 20 storms, and that's what is in part B here. You'll notice that there's a gap because there were a few years when the top 20 storms don't occur during this time period, or you can identify what's the largest storm in each of the 20 years. And sometimes how you organize the data is going to have an impact on the eventual statistics. Like if you're developing the return period, actually what you're supposed to do is you're supposed to look at the top 20 storms over the time period, not the biggest storm in each of the 20 years. And so annual maxima, it's interesting to look at what's the biggest storm in each of the year, but when you're developing calculations related to probability, it's actually the annual exceedance series that you're using to generate the return period storm. So there's a lot of natural disasters that can cause damage to society. There's tornadoes and wildfire and earthquakes and big fake tsunamis. This is, I think, a photoshopped picture here. That's not real. But the only sort of natural disaster that we have a real risk of in West Virginia is flooding. Although it seems like there have been a couple of minor tornadoes recently that's a bit surprising. Here is a hurricane that caused a lot of direct damage and then also flooding. It happened back in 1900, and it went through Galveston, Texas. It was a huge hurricane that back in those days they were really unprepared for storms because they didn't have the same sort of communication and observation systems that we do now. People weren't able to turn on the TV and know what's going to happen in a week. You know, these hurricanes nowadays, they're able to see them coming and evacuate people when they're needed. But in the case of Galveston, this was a big storm that caused 145-mile-an-hour winds, and ultimately there were 8,000 people who were killed, mostly from drowning. You can see some of the wreckage that was caused in Galveston, and actually one of my ancestors lived in Galveston at the time, and after this big storm he moved to California, so I sort of have a direct interest in the storm. The storm surge is 15 feet, and Galveston is on an offshore island that its highest point is 8.7 feet, and so the storm surge was actually, it completely inundated the island. There were some structures where maybe the top of the roof wasn't underwater, but the water that came in was completely overwhelming, and that's why there was so much damage. They later on put in an enormous seawall to try and brunt the effects of the storm surge, but it was too late. Businesses started leaving Galveston. At the time, it was one of the largest cities in Texas, and it's never recovered since that enormous storm. And it's just sort of an interesting case study in not only the loss of life that can be caused from flooding and big storms like this, but also the idea of indirect damage, where the city that previously was one of the largest in Texas is now not even, I think, in the top 10, because people have a perception that it's vulnerable to storms and they don't want to relocate businesses there because of the interruption that the storms could cause. Here's another storm event that was pretty notable. This happened in the spring of 1983, and this is downtown Salt Lake City. And you can notice that there are sandbags along, this is Main Street in Salt Lake City, and there was so much runoff from the mountains. The snowpack warmed up really quickly, and so there was a lot of runoff from the snowpack, and that at the same time there was a couple of rainstorms that just made the rivers overflow, and so they had to find some place for the water to go, and rather than having it flood all of the downtown area, they actually redirected some of the streams that went through the city just along Main Street and then towards the Great Salt Lake. So it was kind of like an event. People would come and see the water flowing down Main Street, and little kids would reach in and play around with the water. Actually, most of the sandbags were filled by volunteers. They just told everybody in town, come out and help us fill sandbags, and so that's what they did. And it's not just Texas and Utah that have flooding. West Virginia actually suffers a lot from flooding because it's so common for people to live very close to the creek. That's one of the few places in West Virginia where you can consistently find flat ground is adjacent to the creek, but then the problem with that is that it's flat ground, but it's so close to an area that's threatened by flooding. Here are some aerial photos of flooding in Illinois that happened not too many years ago. And you can see these are pretty big houses that are almost totally ruined because of the flooding. In this photo, there is a levee that was supposed to have been protecting against flooding, but it's been broken. Agricultural areas can be threatened from flooding, and when something like this happens, it has really unexpected effects where a flood, even just a flood that only affects maybe 5 or 10% of farmlands in a certain state, can have a huge impact on crop prices. It can raise the price of corn or wheat, and then that affects the price of meat, and it's kind of a snowball effect how flooding can affect people far, on the other end of the globe where the markets these days are global. Here's some pictures of flooding just in West Virginia, and you can see that there's a lot of mud that's been transported. That mud wasn't there before the flooding. It got transported because when the water is moving very quickly, it suspends the sediments that normally are setting on the bottom of the channel. And so it's got a bunch of silt and clay and sediments in the water, and then when the water starts slowing down, all those particles settle to the bottom, and then they're just left and they have to be shoveled out. You can see that this guy's foundation has been eroded as the stream just starts getting wider and wider as the water scours the edges of the stream, and now he's wondering if his house is going to start to crack and fall in. Transportation can be interrupted. Anybody who's tried to leave Huntington during a big storm knows that we've got a number of underpasses going under the railroad tracks. There's one at 8th, 10th, Hal Greer, and when they're full of water, it's almost like you can't get out of town because 3rd Avenue gets totally full of water. And really, I found it out the hard way. The only way to leave Huntington when there's really a lot of flooding is you have to go to West Huntington and get on the freeway, and then finally, the underpass towards the freeway isn't closed in a big storm event. So there's several places where flooding can be common, and in the homework assignment you're going to turn in on Tuesday, December 2nd, you're going to get a chance to look at the federal maps that are prepared to identify flood zones. Now, all over the United States, the federal government has put together maps that tells you what's the risk of flooding in a certain location you're interested in. So before you buy a house, you can look up the location on the map and see what the flood risk is. And then that's, of course, going to have an impact on the price of flood insurance if you choose to get that. Along rivers, streams, coastal areas, we haven't had any pictures of alluvial fans. And an alluvial fan is the area at the mouth of a canyon. We'll have a diagram of an alluvial fan in a minute, but it's mostly in really mountainous areas out in the west that they would have alluvial fan flooding. The type of flooding that we see more commonly around here would be those that are along streams and rivers. There can be issues of flooding when there's ground failure, meaning like sinkholes or just areas that are subject to seepage. If there's water flowing underneath an area and it's gradually carrying away the soil that's underneath a structure, then the structure can collapse. And that's sometimes what happens with culverts, is that there's a high amount of seepage under the road as the pore water pressure is very high. Structural measures, what we mean by structural in the case of flood control, we're talking about levees, water bypass. By structure, they don't mean buildings. They mean sort of a man-made system for retaining water or changing where it goes. And so any place you've got a levee, like is pretty common in the Netherlands, they've got all sorts of levees there. Well, if the levee fails, then that can be a flood location. So any sort of area that there's been dredging or they've tried to change how the water flows or how frequently, the water's at a certain depth, and there's a possibility of flooding there. There's a couple of terms that's important for you to learn, and if we go back to the concept inventory that I gave you at the beginning of the semester, each of these terms are on that concept inventory. And since we're getting close to the final exam, it might be worthwhile to start going through that concept inventory and refreshing your memory on those definitions if it's been a while since you looked at some of the terms from earlier in the semester. So a floodplain is just that flat area that's adjacent to streams, rivers, bays, oceans. It's the area that is going to be most commonly flooded when there's a big storm event. And you can see that here is an area with a river, and there's mountains on the side, but then there's a flat area next to the river. And that almost describes Huntington perfectly. You know, we've got hills not far from downtown Huntington, but in Huntington itself it's flat, and the reason for Huntington being a flat area is because it's a floodplain of the Ohio River. And so they've put up a flood wall around Huntington to try and protect it from the Ohio River when there's big flows. But the reason it's flat here is that when the water levels were high, it sort of scoured down the hills that used to be in this area. So it's a floodplain that we're in. And you can see that the floodplain can be broken into different parts. And in this diagram, they're showing you where the stream usually is. This is the typical channel for the stream, and then when you have a 10-year storm, you can delineate how high the water level gets and therefore how much of the land is covered by water during a 10-year storm. You can see what the limits of the water are during a 100-year storm, and so on. And likewise, if you took a cross-sectional view, you know what the water depth is for the 10-year storm, for the 100-year storm, and so on. The assignment that you're going to do for Tuesday, December 2nd, you're going to look up a couple of addresses in Huntington. And I give you two addresses, and I'll just give you a hint on the homework. One of them is in one flood classification, and one is in another. They have two different flood classifications, and it's related to how close they are to the river. And it's not just distance, how close they are to the river, but you'll notice here that the floodplain is wider than the floodplain is here. And that's probably because the ground is more steep in the area where the floodplain is kind of narrow, and the ground slope is more shallow in the area where the floodplain is wide. And so maps like this are used to influence the flood classification that the government gives to properties when FEMA is calculating the risk of having flooding at a certain time. So here's the alluvial fan, and a picture of one coming out of a mountainous area. The way that you can tell it's an alluvial fan is it kind of looks like a delta. You've heard of the Mississippi River Delta. You know, in Louisiana, the Mississippi River empties out into the ocean, and all of the sediment that's being carried by the river gets just dumped into the ocean because the river water that's carrying sediment slows down as it discharges into the ocean, and then all the sediment it was carrying settles to the bottom. And the same thing is true here in alluvial fan. As the water's flowing through the mountains, it's moving very, very fast because, you know, the channel slope in and among the mountains is steep. You know, maybe you'd have a 4 or a 5% slope in a mountain stream, and then suddenly you hit the valley. And when you get to the valley, the slope decreases, the velocity of the water slows down, and so the water isn't able to maintain the same sediment load as it was before, and so it sort of discharges all of those sediments onto the valley floor at the mouth of a canyon. So this is an illustration of an alluvial fan and how that sediment transport effect works. Here's some more terminology that it's important to be acquainted with. And there's a floodplain manager in each county in the United States. Cabell County has a floodplain manager, and his job is to make sure that people aren't building in regulated areas. And so encroachment is the process of putting things in places where they shouldn't be. And if if you think about, this is a cross-sectional area that's showing, the main channel. This is where the water normally is, but then the water level rises as the flow rate increases. If you fill in the area here, you can see that there's this hashed in area on both sides. It's where people have put additional soil to try and get more flat ground that they can build on. If they expanded even further, if you see this person in the home, if they wanted a bigger backyard, people do this all the time around here. They'll say fill wanted. They'll put a sign out in their front yard and they'll ask people to bring dirt, So if this person put more and more dirt and started filling in, let me raise the screen just so I can make it even more obvious what the effect would be. This person's dumping more dirt, and so now it's like this. So during a 100-year storm, when you've added more soil to reduce the cross-sectional area of the channel, then the water level is actually going to get higher in the same storm. So normally the 100-year storm would maybe be at this level if this newly hatched area wasn't filled in. But the more encroachment you do, you're basically reducing the cross-sectional area of the channel, and so you're forcing the water level to get higher, and then it causes more flood damage. And so encroachment is something that we really have to be pretty careful to avoid, because it can worsen the probability of a storm causing flooding, and it also worsens the actual effect of flooding when the storm does occur. So the floodway is the zone that has to be kept clear. So you'll notice here it's indicated in green, no development is allowed inside of the floodway. So technically this shaded area here should be removed. It seems like they've went a little bit further with their development than they ought to have. Where you can build is in the flood fringe. So the floodway fringe is the part of the floodplain that can be constructed in, and still the 100-year floodway, the rise in elevation is restricted to 1 foot beyond where it used to be. So this bottom line is before there was any development, this is the elevation of where a 100-year storm would cause the water level to be in what they're calling the base flood. The base flood is back before there was any development. They ask, where would the water level be? And they say, it's okay to build in the floodplain a little bit. We want the water level to be no more than 1 foot higher of where it used to be. And so then they look at how much of this cross-sectional area can be reduced and cause the water level to only rise 1 foot. And that's how they define what is the floodway fringe. The fringe, the areas on the outside, is where actually it's okay to do a little bit of development. When you are managing a floodplain, there are a couple of priorities, and the priorities here are numbered actually in order. And it's kind of, there's been a lot of analysis and news reports lately when there's been some big storms like Hurricane Sandy. The New York Times did a big article saying how politicians hardly ever do 1 and 2 because it's so much more glamorous to do number 3. When you're managing like a flood, it makes you look like a good politician if you're helping people who have had flood damage. You know, if you're providing aid, then that's what you can get in a newspaper picture and make it seem like you're a compassionate politician and that you're responding to the issues. But when it gets to the point of number 3, it's too late. The opportunity to fix the problem before it even occurs, number 1 and number 2, that's not a very glamorous thing. Voters aren't going to say, I really like that politician because he had a bill that reduced the probability of flooding. People don't think in terms of probability, and preventing problems, it's not something that most people respond to because it's an issue that didn't affect them. You can't impress people with the problems that they didn't experience. And so it's sort of a pity in a way, because if you spend $1 on prevention, you can save $10 or $20 of damage. But spending money on prevention is so much less visible that a lot of times it's neglected when it comes to the priorities of the government. Yeah. They think it's pointless. Yeah, they'll say, you know, they put in that levee, and the water levels haven't got that high the whole time I've lived here. I've lived here 12 years, and I've never seen the water levels that high. And they're just not thinking in terms of probability. Yeah, that's exactly right. They see it as wasteful. So really, the opportunity for smart spending is trying to reduce the susceptibility of an area to flood, or modifying the flood, trying to bring it so that the water levels are lower when the storm actually occurs. So the government subsidizes flood insurance, and that's another thing that's been in the news a lot, is people are starting to ask, maybe the federal government shouldn't encourage people to live in risky areas, because that's what this flood insurance program is it's a subsidy that allows people to live in areas that if they had to bear the full financial risk of their being there, they might not do it. You know, people wouldn't build a big house along the Ohio River if they were going to lose their property and not get reimbursed if the floodwaters came up. A lot of people who build big houses along the Ohio River, they have federally subsidized flood insurance, and if there's a flood, then they get a new house. So why not build there, you know? You got to pay a couple $100 every year, but that's not so bad. You get a nice view. The flood insurance program, in theory, is supposed to have some pretty strict regulations that have to be followed in order for the federal subsidies to apply for flood insurance. They require that a county floodplain manager issue permits, so there has to be a permitting system. Before you build a house, they have to analyze whether you're inside the floodplain or outside of the floodplain. The floodplain manager is supposed to make sure that homes that are at risk are using flood-resistant materials, and so that can be building materials that, if they get wet, dry out more easily. It can be vented basements. There are some structures that are built specifically so that when the floodwaters come up, actually the water can move in and move out of the structure without breaking apart the blocks, basically putting someplace into the structure that the water is designed to flow through, rather than scouring or damaging the foundation of the building. The floodplain manager is supposed to look for ways to minimize damage, and so that might be elevating the structure, maybe putting in a garage on the ground floor and building above that ground floor, you know, putting the habited areas higher, because that's usually where the most value of the structure is, people's furnishings and the expensive building materials are where the people are living. And then also a really important thing is that the floodplain manager is supposed to be prohibiting encroachments. And as I drive around Campbell County, I wonder if maybe the floodplain manager is busy, because it doesn't seem like they're doing a lot to prohibit encroachments. Everywhere I see, there's people expanding their backyards and putting in more fill, and I know one guy pretty well, the guy who works on my truck, just, you know, some hillbilly mechanic, good old boy. I like him a lot, but he's quadrupled the area of his lot in the last 3 years, and I'm pretty sure he didn't go get a permit first. You know, it's just anytime somebody's got extra soil, he puts it in his backyard, and so it makes me wonder if prohibiting encroachments around here is really a priority. It ought to be, because the more encroachment there is, the worse the flooding is. All right, I'm going to show you 3 figures, and these are the 3 most important things of today's lecture. So if you only learn 3 things today, these are the 3 things that you should learn, because they will be on the final exam. Will. All right. This is the way that floods can be managed. There's 3 different curves, and it's important to understand and be able to explain the theory behind each of these curves. And so the first one is look at the x and the y figures here. So the x and y axis. Exceedance frequency versus discharge. Okay, so a certain storm frequency causes a certain flow rate. So this is what comes out of a hydrologic model. You've just been using WMS, right? And I told you to use a 3.2-inch storm for your analysis. And was that a 25-year storm? Did I say in the homework assignment that that's a 25-year storm? Okay, so basically, your model that you developed is able to characterize this curve. It says, for a 2-year storm, what's the flow rate? For a 5-year storm, what's the flow rate? So you could put, like exceedance frequency, that is, like 2-year, 5-year, 10-year, 25-year. That's on the x-axis. And then on the vertical axis is flow rate Q, discharge. So you have to do a hydraulic analysis to understand what this curve looks like. That's the first step of floodplain management. The next step is to find out, for a certain flow rate, how deep is the water level going to be. And this is actually what you do with hydraulic analysis. So for all the range of flow rates that you came up with in this first stage, what you're doing now is finding out what's the depth. So here where it says stage, in parentheses, maybe you should say water depth. And the units for that is feet. It's very important to maybe understand the units for each one of these. Exceedance frequency, the units was years. 2-year storm, 5-year storm, 10-year storm, and so on. Discharge, or flow rate, the units there would be cubic feet per second, or cubic meters per second. Okay, so those were the units of these two figures. So it's basically a chain reaction. Remember, we've talked about how the hydrologic analysis feeds into the hydraulic analysis. And here is why that relationship exists, why a hydrologist hands the data over to the hydraulic analyst, is that the hydraulic analyst is going to find out how deep is the water. And so the way they do that is they look at, all right, so you've got a certain flow rate. You'd use Manning's equation. And you'd find out, for a certain channel width, B, and a certain side slope, 1 to T, you're going to try and find out what is the depth, Y. That's what the hydraulic designer is going to be. And the reason why it matters, the stage, they call that stage, how deep is the water, is because maybe at a certain depth, here's the house. And so the hydraulic designer is going to find out how big of the storm. Does it take a 100-year storm before the water level gets to the house? Does it take a 200-year storm before the water level gets to the house? That's the question that is coming up so far in the analysis. Now the last step, there's 3 curves like I said. The last step is you have to know, for a certain depth, what is the damage that it causes. And I really wish that the axes were switched here, because in all the previous ones, the input is on the x-axis and the output is on the y-axis. So, like, the input of the hydrologic analysis is 2-year storm or 5-year storm, and what comes out of that model is the flow rate. That's your hydrograph. What goes into the hydraulic analysis is the flow rate, and what comes out of the hydraulic analysis is the depth of the water. The economic analysis, what goes in is the hydraulic designer will take the data and give it to an economist. And the economic analysis says, all right, if the water level is 10 feet, there's no damage. If the water level is 11 feet, then the economic analysis looks at how many houses are going to be damaged if the water level gets to 11 feet and says, oh, maybe $1 million worth of damage if the water level gets to 11 feet. And if the water level gets to 12 feet, maybe $3 million worth of damage, and so on. So it's just, the economic analysis is making a curve for how deep is the water versus how much is the cost of the damage that's caused by the flooding. Any questions about this? So this is, you have to be able to explain these 3 curves and actually draw them from scratch, from your mind. Yeah.
Once you have these 3,
Yeah, you could combine them. So you could just jump straight to the chase. Yeah, you can say a 2-year storm is going to cause no damage. A 5-year storm, $1 million of damage. Exactly. You can make a curve like that. So what do you think we want to do? If we made a curve like that, if we said, all right, so exceedance frequency, and so here's 2-year, 5-year, 10-year, 25-year, and then here's damage. And this is $1 million. 2, 4, 6, 8. Okay, so let's say that there's no damage from a 2-year storm, but a 5-year storm costs $2 million damage, a 10-year storm costs more, 25-year costs more. So when we have a curve like this and it says how much damage there is for a certain size storm, what's the logical thing to do? If you know that there's going to be a certain amount of flooding the way things are now, and it's going to cost you a certain amount of money. You know, we're engineers, we like to build things. So what should we do when we look at this as a problem? This is actually a problem statement. You could think of this graph as a problem statement. And so the problem is every 5 years we have $2 million worth of flood damage. The problem is every 10 years there's a big flood that comes through the downtown area and it costs $5 million worth of damage. Every 10 years we're wasting $5 million worth of damage. And so that's the problem statement for the engineer. And the engineer looks at that and says, well, let's try and do something about it. So the next several slides I'm going to show you is different reactions, different ways of trying to modify this curve. You know, the engineer says, maybe we can do something to save money. Think of a modification that could alter each of the above relationships. So what can the engineer do to change what the flow rate is going to be for a certain exceedance frequency? So you've been doing WMS. What sorts of things changes this relationship, exceedance frequency versus discharge? It has to do with the watershed and the rainfall. The engineer can't change the rainfall. The rain is just going to happen when it happens. Okay, less urbanization, or when urbanization has occurred, okay, put the water somewhere else, like in a pond. And so if you put in a retention pond to try and remember all the things we're trying to do is we're trying to slow down the water and increase infiltration. So maybe we could disconnect people's roof drains and try and put in little like rain garden next to their house with amended soil and try and get the water seeping down into the soil. So that's a modification where what we would want to do is we want to bring that curve down. Because remember, water is bad, runoff is bad, it just causes damage and it's going to lead to higher costs in that last economic analysis. And so what an engineer could do is try and find ways to reduce the discharge for a certain exceedance frequency. So curve number, if you remember curve number, that is what you were doing in WMS that was the combination of soil type and land use. And so you can try and restrict urbanization. And they're doing a little bit of that in Huntington nowadays. They're starting to charge a stormwater fee. The new athletic practice facility by the football field, they had to put in a big underground rainwater storage vault to try and hold on to the first inch of runoff. And I think they also have to pay a stormwater fee. It's a little bit unclear to me, but they're trying to discourage people from just paving everything, you know, because when there's lots of parking lots and roads, that increases the curve number and it makes that curve higher. So maybe in your notes you should say the good thing is for this curve to be low. This first curve, low is good because remember, runoff is a problem in the eyes of an engineer. Maybe in the eyes of a farmer, runoff is a good thing because they can use it to irrigate their crops, but we're looking at water as a problem that's causing flooding and it's ripping up the stream. And so urbanization is going to make that curve higher. the engineer is going to look for some sort of a way to make that curve lower. So it could be the ponds, enhancing infiltration, restricting urbanization, and so on. Okay, so what about this next one? What kind of a modification can we make so that for a certain flow rate, the water level is lower than it normally would be? So the hydraulic analysis is when we were trying to find out, what's the depth for a certain flow rate? What sort of problem solving can we do to make that water level lower than it otherwise would be? That's right. Yeah, you can widen the channel because the more cross-sectional width you've got, the less the depth needs to be. So you can make the channel wider, or dredging. You've maybe heard of dredging before. That's when they're scooping the bottom of the river, and so they're just actually lowering the river by scooping out the soil underneath the river. So that's dredging, is just getting rid of the extra sediment that's underneath the river. So dredging, widening. You can try and increase the velocity through the stream, because the faster the velocity, then for a certain flow rate, the shallower the depth will be. So you can increase the velocity by making it smoother. Like if you put a concrete channel in, it's going to have a higher hydraulic efficiency than if the channel is lined with grass. Because grass has a higher N value, Manning's roughness coefficient. So anything that's going to improve the hydraulic efficiency. So what do we want in this curve? Remember, I was saying in the first curve, we want it to be lower. This curve, we want it to be low. We want the water to be really shallow. That's best for us, is the more shallow the water is, the less likely it is to get out of its banks and start causing damage. All right, and then the last thing is the relationship between damage and stage. So when the water level gets to a certain elevation, how much money damage is it going to cause? And the sort of modification that you can make for that is you can either tell people to get out of the flood area, like don't let millionaires build homes right next to the Ohio River because it's foolish and the river's always going to overflow. It's just a matter of time. Or you can raise people's houses so that there's less damage at a certain stage. So we're going to go through and look at some of the structural measures first. Structural measures just basically means facilities like a reservoir, a diversion, a levee, dike, channel modifications, like the things where you're going to go get some machines and you're going to go have a project. That's a structural measure, the sort of thing that you need a backhoe and you're stamping plans. Non-structural measures is just ways of trying to modify people's behavior. Rather than building something, a non-structural measure is kind of like the soft changes, asking people to move or asking them to put a garage on the ground level rather than occupying the ground level, because maybe the ground level is going to get flooded. All right, so we'll talk about both of them, but we'll begin with the structural measures. And here's one. It's the flood control reservoir. So I've provided those three figures, the stage to damage, stage to discharge, and discharge exceedance frequency. And what the flood control reservoir is going to do is it is going to make a change to the exceedance frequency versus discharge curve. It leaves the other curve steady, but here's the before. The solid line is before, the dashed line is after. So let's look at what does putting in a big reservoir actually do. For a certain size storm, it's having the water level coming through the river be lower than it normally would, except for they're showing in this case it's a little bit higher for the small storm. And I think what they're getting at with that is they're saying, well, there's always going to be water inside of the reservoir. So even with the small storm, you're going to have water coming out of the reservoir. It's kind of flattening out the flow rate. And so it's, you can think of this as a big pond. And this is a really big pond because that looks like a pretty big reservoir there. But it's reducing the peak magnitude, and instead of the hydrograph all of a sudden You are looking at hydrographs in your WMS assignment that were very flashy in most cases. It's trying to take that really flashy hydrograph and smoothing it out a little bit. Longer period of discharge where this is time and this is flow rate. If you reduce the peak flow rate by having a storm, then that's going to mean that in any particular time, the stage is going to be lower than it would have been, and so there's a lower risk of flood damage as well. The disadvantages of using a reservoir is that this pond can fill up with sediments because the water coming into the pond or the reservoir has a lot of silt and clay and sand, and when it gets into the pond, the water is stationary, and so it actually acts as a trap, and so over time they can fill up with sediment and sometimes have to be maintained, and the pond has to be dredged to react to the sediment deposition. And then the other thing about it is that putting this in isn't going to mean that people don't continue to build expensive things downstream. So even though maybe you're fixing this issue, over time, just land gets more and more developed because populations are growing and people are spreading out to the suburbs. Like, here in Huntington, not nobody, but the trend is for people to live in the suburbs. People are starting to live in Barbersville and beyond Barbersville, even though there's still plenty of vacant homes and empty land inside the city limits. We just keep expanding and tearing down forests, and that's urbanization. And so the main disadvantage of flood control measures like this is that you can fix the exceedant frequency versus discharge curve, but then people continue to put expensive things in the flood zone. You really haven't solved any problem. There are certain types of cases where a reservoir is suitable, and for each of these structural measures, some of them have common suitability constraints, and a few of these constraints are unique. I've just highlighted, for example, that a reservoir is good if you've got a really large area that you need to protect. And so you're putting all of the extra water in one place, and in theory you're protecting a large tract of land that otherwise would have a little bit of flooding on it. And so it's spread over a large geographic area. That's when you'd want to use a reservoir. If you want a lot of protection, there's a variety of property types and so on. I won't read through the list, but I'll point out some of the differences compared to the reservoir when we look at other structural measures in the following slides. So here's another one, is a diversion. So in a diversion, what you're trying to do is you're rerouting the water away from a really risky area. The idea of a diversion would maybe be if we were trying to protect Huntington, what we have right now is a flood wall. But what they could do, instead of a flood wall, a diversion could be used like this. If here's the river, and then you've got the town, then you could have the water go around the town by putting in some extra channel here, sort of like extra capacity. And so you could basically, most of the time the water is flowing this way, but then when the water level gets to a certain area, then this bypass kicks in, and so it would mean that between the inlet to the bypass and the outlet to the bypass, the water level next to the town is kept lower than it ordinarily would be. So this is the idea of a bypass. And so what a bypass does is it modifies the exceedant frequency versus discharge curve, because it says that for a certain size storm, the flow rate is getting higher and higher and higher, the flow rate through the river. So the flow rate is gradually increasing, but then all of a sudden it plateaus. And so that means you have a 5-year storm and a 25-year storm, and there's the same flow rate going next to the town because all the extra flow is going through this diversion in that flat part. This flat section here is how much extra water is carried by the diversion, but then all of a sudden the diversion is full. Once this diversion can't handle any more water, then the extra water is still going to go through the main channel, and then that's why this starts getting sloped again. And in fact, it's even steeper than it was before, because the diversion, in theory, can start backing up a little bit and causing more problems than it can solve. So the diversion has the same disadvantage as the reservoir in that people get a false sense of protection, and when they hear that you've put in something to control the river, then they'll start building along the river, and so there's expensive property near the waterfront because everyone wants a beautiful view of the river. And so now all of a sudden, all the economic benefit of reducing the frequency of flooding is counterbalanced by more expensive properties being put into the flood zone, and so you only sort of temporarily solved the problem. So a diversion is likewise the same as with a reservoir, suitable if you've got a large area and you want a lot of protection. But one of the really important things to look at when you're considering whether to use a diversion is whether the value of the damageable property justifies the construction costs, because these can be very costly to put in diversion, and so the analysis of how much money is going to be saved versus how much it costs, plus the time value of money and the probability of the damage occurring, it's a complicated sort of analysis that has to be done. Here's a picture of a levee. Let me dim the light so you can see that a bit better. Okay, in the picture of the levee, you can notice that here's a roof, and the roof level is at about the same elevation as the river. And so a levee is a big earthen wall that allows water to be conveyed, and then you can develop the property that's lower than the water line. And ordinarily you wouldn't be able to do that. You know, usually rivers are below the population center. When you've got a levee, then you can have the population center lower than the water surface elevation. So this is going to modify all three of the curves. Remember, we're talking in terms of these three curves, and so the levee has the advantage of, number one, it changes the exceedance frequency versus discharge. The solid line is before, and the dashed line is after. So all of a sudden we've got a paradox, because remember what I said is all of these structural measures we do, we're trying to bring the new line should be lower than the old one. So why do you think that a levee is going to make the discharge higher than it would have been in the past for a certain size storm? And like what it's saying is the 10-year storm used to have maybe 20 cubic meters per second, but now that same return period storm has 25 cubic meters per second. Why is there a higher flow rate than there used to be in the case of a levee? It's decreasing the area the water can go. Yes, that's right. And so what that means is that the peaks flow through more quickly. So let's draw a little diagram here. Before the levee, maybe it was like this. You know, the water would flow like that. But they say, well, we want to build around here, so instead of having the water there, let's do this. Let's put in a big levee like that, and this is exaggerating things, obviously. If we put in the levee, then the water level will be here, and then we can put in crops down here, or we can build a house there. And so now more of the flow area is far away from this frictional surface, and so it's increasing the flow rate. For a certain size storm, you get actually a higher flow rate going through the channel than you would before. Because previously, before the levee was put into place, there was more resistance to flow. Okay, so we kind of shoot ourselves in the foot a little bit with this first curve here, the exceedance frequency versus discharge. But now, let's look at the next one. For a certain discharge, the stage is higher. Again, it does kind of the opposite of what we'd want, because not only is there more flow going through, but the water level is higher than it used to be, right? Because remember, in the past, before the levee was there, our water level was down here. This was our original water level. So we forced the water level a little bit higher. but not to fear. It makes a big change in damage versus stage. So just because of where the water is, you know, the water used to damage all of this area in this fringe, and now it's protected. And so the whole point of a levee is that it reduces the amount of damage that there is for a certain water depth. And here's some pictures of the flood wall that we've got in Huntington. You know, it's just walking distance from here. Harris Riverfront Park, you can go there. You'd see there's the gates. They have to drop in the gates manually when they have a projection that the river is going to get too high. And here's a photo of the flood wall actually holding back the river. Channel modifications is another way of improving the resistance to flooding, and that is just dredging. This is a dredging barge that's going through a river, or trying to straighten out a channel to improve its hydraulic capacity is another example of a channel modification. In Europe, sometimes they will put in dams in harbors so that a storm surge doesn't cause flooding and damage. You know, if a hurricane occurs or just wind-driven waves can raise the water elevation, they want to keep those out, then they can raise these gates so that the water is higher on one side of the gate, but then on the other side of the gate, close to the harbor and where all of the urban areas are, is below, the water level is lower. Channel modifications raises the curve here, which is bad, decreases the amount of storage that there is, but it also lowers the water level, which is, this is where the improvement is in the middle curve, because it reduces the depth of water for a certain flow rate. All right, lastly, let's just look at this slide, floodproofing. Floodproofing is trying to use materials that can be dried out. You know, instead of drywall, you know, once drywall gets wet, it's ruined, basically. It's going to get mildew and it has to be completely replaced. But there are building materials that are more resistant to flooding, like a cinder block. You know, if a cinder block gets wet, it's not going to immediately need to be replaced. And so choosing building materials that are suitable for a flood-prone area, it doesn't, just doing this in isolation doesn't change the hydraulics or the hydrology at all, but what it changes is if the water level gets to a certain depth, how much damage there's going to be. And so what it's showing is that, you know, for a certain depth, instead of a lot of damage, you're having less damage. If you use cinder blocks instead of drywall, when the water level comes up through your house, you're not having to replace all that drywall, so there's less damage for a certain depth. You're trying to, in other words, ruggedize the house so that there isn't quite the same cost that there otherwise would be. I'm going to save this slide for next time. We'll look at this slide next time, but I do want to show you a picture of a car. This is a car in New Orleans, and it's because of the flooding that happened in New Orleans back in 2005. I think it was called Hurricane Katrina, right? Do you remember Hurricane Katrina? A lot of people moved away from New Orleans and never came back after that storm because they realized that it's just a risky place to live. So businesses relocated and didn't come back. And that's an illustration of some of the kind of indirect damage. When it's leaving behind mud and sediment, it's just kind of, it doesn't look very good. It interrupts business and it drives people away. So it's not just always about the direct cost of damage, but also indirect costs as well. We'll talk more about that on Thursday and get into the weeds on the calculations. Bring your computers on Thursday because we're going to do some Excel. All right? I will see you then.